given here is this famous historical traditional theorem. What does it say? It says the following. The determinant of a matrix A can be obtained by selecting any row and computing the following quantity. What quantity? Hold on to your hats, sit down if you have to, okay? This is how to compute the determinant using this Laplace expansion theorem. What you can do is first of all, you look at all of the entries in that row I, okay? So it'll be AI1, AI2, AI3, etc. Okay? Then you multiply each of them by the corresponding cofactor. So you drop the row and the column to which Aij belongs and compute the determinant of what's left and multiply by that power of -1 according to the formula. Then you add them all up. Okay? And that simple procedure gives you the determinant. Okay? So if you thought that using row operations was a bit complicated, this is even worse, believe me. Okay. So let me give you simple examples just to try and make this a little bit clearer. Okay, so let's see, we have a matrix like that. So it will look like this one. It's just a simple situation. So first of all, we have to select a row, and according to this theorem, we can pick any row we want, and we're always going to end up with the correct determinant. Okay, so let's pick the second row. Okay, so what we're going to do is, first of all, we're going to use the 3 entries of the second row. So we're going to write those 3 entries there. Then what we're going to do is we're going to figure out for each of them, should we put a negative in front of the number or not. So remember, we start with the positive with a positive value in the top left corner, and then we change sign every time we move horizontally or vertically. So to go from the top left corner down to A21, we move vertically once. So that means that in front of A21 we need a minus. Okay. Then in front of A22, well, A22 is in the same diagonal as A11, or if you want, you can simply figure out that -1 to the power 2 plus 2 is +1, so we need a plus. Okay, and on top of in front of A23, again, we need a minus. Then what we're going to do is we're going to multiply each of these by the corresponding cofactor. So for A21, we're going to multiply the determinant of the minor. The cofactor includes the -1 to the power. So we're multiplying that by the determinant of the minor, which consists of A12, A13, A32, and A33. Notice that in this situation we have eliminated the second row and the first column, and so that's what's left. For A22, we eliminate the second row and the second column, and this is what is left. And then for A23, we eliminate the second row and the third column, and this is what is left. Now, one thing to notice here is that we haven't really computed the determinant. All we have done is we have rewritten the determinant in terms of smaller determinants, and that's really what that theorem allows us to do. Now we have to keep going. We're not done yet. So imagine trying to apply this theorem to a larger matrix. Every time we're going to decrease the size of the matrices by 1, but also every time we're going to end up with more and more of these determinants to compute. Okay. Now, however, as I said, this theorem is fairly powerful, and in fact it has another version of it. So the same Laplace expansion theorem says that the determinant of a matrix can be obtained by selecting any column Cj and computing the quantity. Okay, we're going this time to compute this thing as the sum with I changing from 1 to n of each of the elements of the column j times the corresponding cofactor. So again, to give an example, if this is our determinant that we're trying to to compute, this time I'm going to select the third column. Remember, the theorem says you can pick any column you want, or, as I said earlier, any row you want. You're always going to end up with the same answer. So if you do that, then the determinant is going to be equal to this long expression. So let's see, what do we have here? We have the 3 elements of that column, A13, A23, A33. Each one of them in front of it has the corresponding sign, plus or minus, depending on what position it is in. And then each one of them is multiplied by the determinant of the corresponding minor. Okay? And once again, we've gone down from a 3 by 3 determinant to 3 2 by 2 determinants. Okay, and we know that 2 by 2 determinants are easy to compute, so we're almost there. But again, keep in mind that computationally speaking, this is a very awkward way to do it. But again, this is the original way. Actually, it's not even the first way in which determinants were computed. They were computed in even more complicated definition. This one was already an improvement, and then the method I showed you, I think it's still an improvement on this one. So is there any good in this Laplace expansion theorem beyond the confusion about minors and cofactors and indices and summations and so on and so on? Well, let's see what's good about it. So what's this good for? Okay. So first of all, just to re-emphasize, not refresh your memory, you just heard about it, but just to re-emphasize, this theorem reduces the computation of a determinant to a sum of smaller determinants. Okay? So that by itself can be an advantage. So we're going from a large determinant to a slightly smaller one. The problem is that we're not going to one smaller one, but to several, except in one case, okay? And that is the one case where this becomes useful is where the matrix has a row or a column with lots of zeros, because then in that expansion that we just saw, most of the terms become zero, because all of those aij, or many of those aij's, will become zero. And so effectively we can use this theorem in order to reduce the complexity of the computation of the determinant, and we're going to see some of those examples in class. So in those situations, this theorem is in fact useful. It is also useful theoretically because remember, it tells us that whether we compute by rows or by columns, it doesn't really make any difference. And we're going to see how that can be used in to prove some other little bits of information and properties about determinants. In general, however, keep in mind row reduction is more efficient, and so unless you see a really good reason, namely lots of zeros, to apply the Laplace expansion theorem, just stick to row reduction.